You know, your brain isn't some fixed, hardwired machine. It's actually a dynamic, living network that physically changes with every single thing you experience. Today, we're going to dive into the incredible process that makes all of this possible, synaptic plasticity. But have you ever really stopped to think about that? How does something as intangible as a memory or learning a new skill actually become a physical part of your brain? How can a fleeting moment lead to a change that lasts a lifetime? That's the central mystery we're tackling.
Well, the answer lies in this absolutely amazing concept, synaptic plasticity. It's the core mechanism that allows the connections between your brain cells, the synapses, to get stronger or weaker depending on how much they're used. And get this, it's not just a metaphor. It's a real, physical rewiring process happening inside your head right now.
Okay, here's a great way to picture it. Imagine all the connections in your brain are like pathways through a dense forest. When you learn something new, you're essentially forging a brand new path. The more you use that path, by practicing a skill or recalling a memory, the wider and clearer it becomes. But what happens if you neglect it? Well, it slowly gets overgrown and just fades back into the forest. So, this constant remodeling of your brain's pathways really boils down to two main rules. For any given connection, there are two possible outcomes. It either gets stronger or it gets weaker. Simple as that. On one side, you've got this strengthening process. It's called long-term potentiation, or LTP for short. This is where that famous saying comes from: neurons that fire together wire together. When two brain cells are active at the same time, the link between them gets a boost. And the opposite? That's called long-term depression, or LTD. This is the use it or lose it rule in action. Connections that are out of sync or just aren't used, they gradually weaken. Now, to actually see this process in action, scientists turned to a pretty surprising teacher, the humble sea slug. Seriously, this little creature gave us some of the first concrete proof of how learning physically changes the brain. And the Aplysia sea slug is perfect for this kind of research because its nervous system is incredibly simple. We're talking just a few thousand neurons, and they're huge, really easy to identify. This was a total game changer, allowing researchers like Nobel laureate Eric Kandel to literally map out the exact circuits for a behavior and then watch them change as the slug learned. So here's how the experiment worked. At first, a light poke to the slug's siphon makes it pull in its gill. It's just a basic reflex. But if you keep doing it, the slug kind of gets bored. It habituates, and the reflex gets weaker. Then comes the key part. They pair that gentle poke with a mild shock to its tail. Now, the slug is on high alert. And what happens next is amazing. That same gentle touch, all by itself, now triggers a huge, rapid withdrawal. A memory has been formed. That touch might mean danger. And this is the absolute kicker. The slug's behavior didn't just change. Its brain physically changed. The shock caused certain neurons to release a flood of chemical messengers, like serotonin. This boosted the connection between the sensory neuron and the motor neuron, making the signal between them way stronger. Learning was literally written into the physical structure of its synapses. Okay, so that's a sea slug, but what about in our own brains? Let's zoom way into the molecular level and see how this strengthening really happens. It turns out there's a kind of master switch that decides when a connection is important enough to beef up. And that master switch is a molecule called the NMDA receptor. You can think of it like a super smart gatekeeper. It's called a coincidence detector because it will not open its gate unless two very specific things happen at almost the exact same time. It's a really brilliant system. First, the sending neuron releases a chemical signal called glutamate. But that's not enough on its own because a tiny magnesium ion is literally plugging the channel, like a cork in a bottle. The only thing that can pop that cork is a strong jolt of electricity in the receiving neuron. So when both things happen together, the chemical signal arrives and the receiving cell is all fired up, pop, the magnesium cork gets ejected, the gate swings open, and calcium ions flood into the cell. That rush of calcium is the go signal. It kicks off a chain reaction that tells the cell to add more listening posts, these things called AMPA receptors, to that connection. It's kind of like adding more antennas to a radio tower to get a stronger signal. Now, with more of these receptors in place, the synapse becomes way more sensitive, and the entire connection gets stronger and more efficient for the future. So, from sea slugs to tiny molecular switches, what does all of this mean for you? Why does this complicated process matter so much in our day-to-day lives? Honestly, it's everything. Synaptic plasticity is the physical mechanism behind learning to play the piano, mastering a new language, or just remembering your best friend's face. It's how your brain can recover from injury, rerouting connections to work around the damage. It means that your brain is not a static thing. It's a living, evolving network that you are actively shaping every moment of every day.
Every piece of information you take in, every habit you build, every thought you have is physically sculpting the structure of your brain. The person you are today is, in a very real sense, the result of all your brain's synaptic changes. So I guess that leaves one pretty big question. What will you teach it next?